Hello and welcome back to Learning with the Fosters. Today we are going to return to real numbers and the real number line. If you recall our discussion and our lesson about the real number line, we talked about how, among other things, it really helps us organize and look at the real numbers based on some of their properties and some of how they're defined, better than just simply as a set. We spent time looking at it as a set, but if you remember, the set isn't necessarily ordered. But the real numbers are ordered. We looked at how there is relations both relative to each other, that is, one is less than or one is greater than another real number. We looked at inequalities as ways to express that: less than, greater than, less than or equal to, greater than or equal to. And we also talked about how there's some quantitative information built into the real numbers. In other words, a number is not just greater than or less than another real number. How much greater than, how much less than. And we began kind of informally talking about distance as a way to think of that, particularly on the real number line. So today we are going to look at distance between points on the real number line, and also absolute value. Now, you're probably familiar with absolute value, and we'll deal more with absolute value in future lessons as we look at equations and inequalities and other things that involve absolute value. But today we're just going to do enough to kind of help us talk about the distance between the points on a real number line. So again, remember that the real numbers have relative relations to each other. One is greater than, one is less than, or they're equal to. And on the number line, that corresponds to left or right. But also we want to be able to talk about how much greater, how much less than. And part of that is very intuitive, as we kind of, our informal historical discussion of numbers looked at some of the way in which numbers have, or our understanding, our concepts of numbers have developed. When we say we have 5 eggs, we know that that is greater than 2 eggs. Well, how much greater than? Not just kind of some abstract idea, but rather it is precisely 1, 2, 3 more eggs than 2. 5 is 3 greater than 2. So let's motivate this lesson with a little example. You get to see my artistic skills here. So let's say this is our home. This is our car. We're going to go on a trip. We're going to travel some distance. Town A, located over here, is 120 miles. We'll use miles away, but you can use any unit of distance, or even just simply a unit away. But town A, or location A, is 120 miles this direction, little arrow that way, from our home. Town B is this direction and 80 miles. So we're talking about distance. We want to ask ourselves a few things. Remember, this is kind of a way that we can talk about distance. The distance between H, instead of writing home again, we'll just call home, maybe I'll even write it, H. So the distance between H and A, or the distance between our home and town A. Well, our notion of distance and our understanding of distance, that's very easy to know. The sign tells us it's 120 miles down the road. So if we were to mark these, if we're looking at mile markers, this would be mile marker 1, 2, etc. There would be, on the 120th one, we would arrive at our location, town A. Points on the road. Now, there's also, of course, half miles, 3/4 miles, etc., just like we talked about with the rational numbers. The distance between, let's say we wanted to go to town B. Let's say our brother lives in town A, we want to visit him, and our sister lives in town B, we also want to visit her on occasion. So we're going to head this direction, a different direction than town A, but it's 80 miles in this direction. So we could ask, what is the distance between our home and B? Well, again, that's 80 miles, and there would be 1, 2, 3, 4, 5, etc., up to 80. So let's comment on the obvious here. Let's note a few things that we're very used to identifying. They're different directions. Town A is this direction, town B is this direction. Different directions, but distance is always positive. If we drive to town A, our odometer is going to read 120 miles more than it did when we left our home. We drive to town B, our odometer is going to read an additional 80 miles as we get to town B. So distance, and this is very intuitive for us, is always what? It's always positive. We're not going to have a negative distance. We'll translate this to the real number line in just a moment, but if we're kind of already thinking that direction, if town A is in the positive direction, well, that's 120 miles. But then if we travel to town B, that's not negative distance, is it? Our odometer is not going to reverse 80 miles as we turn that way. Otherwise, when it comes time to sell our car, all we have to do is travel in B far enough to erase all those miles off. The distance will keep accumulating positively. If, let's say, we brought a brand new car, we have 0 miles, we travel to town B, we're not going to have negative 80 miles, we're going to have 80 miles on our car. We travel back, that's another 80 miles. Irrelevant of the distance, of the direction we're traveling, the distance is always positive. Well, what if we don't travel anywhere? If we just park the car there, then our distance is 0. So what we can say is that distance, dealing with distance between these towns on this road, is greater than or equal than 0. And again, I don't think that's a new idea for us. We're very familiar with distance as being such. Distance is positive or it is 0. That is if you haven't traveled at all. So let's translate this scenario to the real number line. And again, somewhat state the obvious. So rather than our road with our nice little drawings, we simply have the good old real number line that we've been working with. Here is our home. Instead of a nice sign and a welcoming sign and home, we just simply have point H. Here's town A. We simply have point A. Town B, we simply have point B. Now remember, on the real number line, points correspond to coordinates, or the real numbers. So we can think of the real numbers as points on the real number line. So in this case, because of our scale, this is 10 miles, 20, 30, 40, 50, or simply number. This is 10, 20, 30, 40. This is the point that corresponds to the real number 50. This is the point that would correspond to the real number 75, etc., to the real number 120, forming that correspondence with point A. Same thing with B, but now it's the real number line, so we're moving in the negative direction. Remember, 0 is our origin. That's a good place for our home to be located, at least for this initial problem. So as we move in this direction to town B, we're moving in the negative direction. We're getting less than. This point is less than H, which is 0. This point is negative 10, negative 20, negative 30, negative 40, negative 50, negative 60, negative 70, negative 80, and that is our corresponding point B. So, let's look at these properties and see if they still hold for the real number line. Well, the distance between 0, point H, and A, or 120, so we're looking at the distance between the real number 0 and the real number 120 is what? Well, kind of the same thing we noticed up here. It is 120. So the distance between 0 and 120 is 120. In fact, that's part of the way we think of 120 is the distance from 0 in which it is. Well, how about the distance to our point B, or our real number corresponding our coordinate, negative 80? The distance between 0 and, notice, our real number is negative 80. Negative 80. What is the distance there? Is it going to be negative 80? Well, no. We already talked about how distance doesn't make sense in terms of negative distances. If we're traveling, regardless of direction, we're either not moving, therefore our distance is 0, or we are moving, and that is increasing regardless of direction, so our distance is always positive. Our distance is greater than or equal to 0. So our distance, again, even though we're moving in the negative direction, is a positive 80. So the distance from 0 to 120 is 120, but the distance from 0 to negative 80 is 80, a positive 80. Our distance is always greater than or equal to 0. So let's look at a quick example. Let's have a mock trip here. Let's say we wanted to travel from our home to town A to visit our brother, I think it was. Then we'll have to travel back home, grab a bite to eat, and then travel to town B to see our sister. The question we want to ask ourselves is, what is the total distance that we drive? Now, again, being very familiar with distance, this is like almost, snap of a finger count. All we do is simply add up the distances between these. But let's do the same thing using the real number line as we think about distance. So first of all, we're asking about the distance from H to A, or our distance from our home to town A. What is that? Here's H to town A. We already talked about that is 120 miles. So we have 120 miles. Now we're going to add so we traveled 120 miles from home to town A. Let's say we brought a brand new car. We now have 120 miles on our odometer. Now we want to travel from town A back to home. So we're asking distance from A to home. And that will equal, okay, interesting. Now we're going from A to H instead of H to A. Well, how far are we going to travel? Well, the same amount, right? The distance isn't going to matter simply because we're switching direction. So our distance is, even though we're moving in the negative direction on the real number line, we are moving as we start out. Once we reach this mile marker, the real number 110 is less than 120, but we're still putting positive distance on our car. So our distance from A to H will also be 120. So notice, our distance from H to A is the same as our distance from A to H. And that makes sense in real life. The distance between two towns doesn't change based on our direction that we come and go. Now we arrived back at our home. Now we want to go visit our sister, and I guess we're going to stay with her for a while. So now we're asking the distance between H and B. Well, we talked about that. Even though we're moving in the negative direction into the negative real numbers, our distance is still positive. Our distance is 80. So what is the total mileage that we put on our car? Our odometer would read 120 plus 120 is 240 plus 80, so 320 miles. It's not 120, then minus 120, which would bring us to 0, then minus another 80, which would bring us to negative 80. Our trip, we drove 320 miles, not negative 80 miles. So again, distance, to kind of restate the obvious, is always greater than or equal to 0. Or in other words, distance is always positive, even on the real number line when we're moving in the negative direction.
Hello? I've been with the finger up for a while.
So when talking about distance on the real number line, to use absolute value will really help us do this. So what is absolute value? Well, we're going to look at a geometric description of it and then an algebraic more definition of it. So absolute value of a number, A, we denote it as this. We don't want to write absolute value all the time. So these two vertical bars with the number, the real number, the variable in between, this is saying the absolute value of a number A. And again, remember at this point in our discussion, when we say number unqualified, we're talking about real numbers. So the absolute value of a number A, we denote as such. Let's first look at geometrically, which we've already been doing with our distance example. So a geometric description of the absolute value of a number A, we could say is the distance on the real number line from a number A to 0. Or in other words, just like our town A, the distance between that and 0, that is the absolute value of A. So A, from our last example, was 120 miles from our origin, from our home, that is 0, so the absolute value of town A was 120. Similarly, with our town B, which corresponded to the real number negative 80, the absolute value of our town B was the distance between, on the real number line, from that number B, negative 80, to 0. Well, the distance we noticed was positive. So the absolute value of negative 80 at that last example is equal to 80. The distance on the real number line from a number A to 0. So let's look at a few examples. So the distance between 0 and 2 on the real number line, you can draw this out if you would like, is equal to, the way we can describe that, the absolute value of 2, which is equal to, well, what is the distance between 0 and 2? If we were driving in miles, we would have driven 2 miles. So the distance between 0 and 2 is the absolute value of 2, which is equal to 2. Now, also we notice that this is the same, it's also equal to the distance from 2 to 0. The distance between 0 and 2 is the same as the distance from 2 back to 0. So the absolute value of 2 is 2. Well, what if we look at the distance between 0 and negative 2? Or in other words, the absolute value of, I don't know if you can see that negative sign, the absolute value of negative 2. Well, again, that is 2. If we had our real number line, here's 0, here's negative 1, negative 2. What is the distance from 0 to 2? If we were driving 1 mile, 2 miles, our distance is a positive 2. We traversed 2 miles, or 2 units, or 2 integers in this case. So our distance from 0 to negative 2, which is the absolute value of negative 2, is again equal to 2. And again, we notice that the distance going the other way from starting at negative 2 going to 0 is going to be the same distance as if we started at 0 and went to negative 2. So, absolute value is always greater than or equal to 0 because this is an arbitrary rule that our teachers just made up and decided to make us practice these. No, that's not what it says. That's not why. Absolute value is always greater than or equal to 0 because distance is always greater than or equal to 0. Let's read that one more time. This is important. Because when we're talking about math and these type of things, it's really important to understand part of the reasons why not just our teacher or these math guys decided to make up a symbol like this and say, well, it's always going to be positive simply because we think that'll make a cool math concept and it'll make kids have more homework problems. No, the absolute value is always greater than or equal to 0 because distance is always greater than or equal to 0. The correspondence between distance and absolute value, geometrically as we've been talking about, absolute value is the distance on the real number line from a number A to 0. So therefore, one more time, absolute value is always greater than or equal to 0 because distance is always greater than or equal to 0. Well, let's define this now algebraically. So again, this is how we denote the absolute value. So we can say the absolute value is equal to A if A is greater than or equal to 0, or, and this is kind of a way to give two different cases. So we have if statements. If A is greater than or equal to 0, then the absolute value of A is A. If A is less than 0, then the absolute value of A is negative A. So if you're unfamiliar with this type of notation, let me read through this just one more time. These are conditions. On the real number line, you choose any arbitrary real number. It will fit one of, but not both of these conditions. So if that number A is greater than or equal to 0, then the absolute value of A is what? A. If we choose a real number and that real number is less than 0, then the absolute value of A is equal to negative A. So let's work through a few examples. If you're unfamiliar with kind of algebraic definitions like this, I think these will help. So let's look at this first one. Here's our example. The absolute value of 15 over 16. Well, what does that equal to? So this is A. So is A greater than or equal to 0, or is A less than 0? Well, it's greater than, right? 15 over 16 is almost 1. So this first condition holds. Our A is 15 over 16 is greater than or equal to 0. So the absolute value of that A will equal A. So see, this is the absolute value of A is equal to this condition. So it's equal to A. So what is A? Again, use parentheses for substitution. So let's use yellow chalk here. A, again, is 15 over 16. So the absolute value of 15 over 16 is equal to A itself, 15 over 16. That may seem kind of pointless and dumb at this point, but it's not. This is a very important, absolute value can be very useful and very important. So the absolute value of this particular A is equal to itself, is equal to this particular A, 15 over 16. Why? Because A is greater than or equal to 0. Well, let's look at this one. Here we have the absolute value of A, in this case, negative 27.4. So is this going to be equal to A, or is it going to be equal to negative A? Well, how do we determine that? We have to look and see which one of these conditions A meets. So is our A, negative 27.4, greater than or equal to 0? No, it's less than. So it's this second condition. So the absolute value of A in this case is equal to negative A. And what is our A? So it's equal to negative A, the second condition, and our A is negative 27.4. Okay, well, what is a negative 27.4? Remember, this is like a negative 1 multiplied by negative 27.4. Negative times negative is a positive. So this is equal to positive 27.4. And that makes sense because even though our number is negative, our absolute value geometrically corresponds to distance. Distance is always positive or 0. And so we see that our algebraic definition is working. If we simply mistakenly followed our first criteria, then we would have had the absolute value of negative 27.4 is equal to A. Well, A is negative 27.4. Distance can't be negative. Therefore, this is not what we're talking about with the absolute value. Let's try a few more. What about the absolute value of a variable? Say heart, whatever that is. Well, is it positive or negative? Well, there's no negative, so it's positive. We can substitute this for X or Y or Z or J or whatever. So, the absolute value of A, in this case, A equals heart. So, what is the absolute value of this going to be? Well, it depends on our conditions. Which one does it meet? Is A greater than or less than 0 in this case? Yes, it is. So, therefore, the absolute value of A, or the absolute value of heart, is equal to A. What is A? Heart. The absolute value of heart equals heart. How about the absolute value of negative pi? Well, the absolute value of A is negative pi. In fact, let's write this out so we can keep it in our mind. A is negative pi. That's what A is. So, the absolute value of negative pi will equal either A or negative A, depending on which condition it meets. Is A greater than or equal to 0? No, it's negative. So A is less than 0. So therefore, the absolute value of our negative pi, our A, is equal to what? Negative A. So it's equal to negative. Substitute in our A, which is negative pi. And what does that equal? Well, again, a negative times a negative is a positive. So it's equal to positive pi. And again, we see that our distance is positive. So pi is the distance pi from 0. Negative 27.4 has a distance 27.4 from 0. Distance positive. So we see that the absolute values are always going to be positive algebraically, just like we saw geometrically. Geometrically, the reason is because absolute value is always greater than or equal to 0, because distance is always greater than or equal to 0. Algebraically, we see the absolute value is always going to be greater than or equal to 0 because of these two conditions, our definition of absolute value. Let's try a little more complicated. How about this? Negative absolute value of 7. Well, first of all, let's figure out what our A is so we can follow our algebraic definition. So in this case, A is what? Well, A is what's in between the absolute value. So is A negative 7 or 7? Right, it's 7. This negative sign is on the outside. So our A in this case is 7. Okay, so that's simple enough. So when we come to our understanding of what absolute value is, we're going to figure out what the absolute value of 7 is. Well, is 7 greater than or equal to 0? Yes. So it's this first condition. So therefore, the absolute value of 7 is what? 7. Not too bad. It is A. When A is greater than or equal to 0, the absolute value of A is simply A. It's simply what it was. But we can't forget to bring down this negative sign, right? Negative, like a negative 1 times a 7. So negative 7 is our answer. Now, I thought we just said we can't have a negative number for absolute value. Well, we didn't. The absolute value is separate from, or it's an embedded relation with respect to this negative sign. Remember, like when we're doing the order of operations, we do our grouping symbols first, and we mentioned that absolute value was a grouping symbol. Well, this is in part why, because we're figuring out what the absolute value of whatever occurs in between these bars is. And then in this case, we have this negative, or this implicit negative 1 multiplied by the absolute value of 7. So we're not saying the absolute value of 7 is negative 7. What we're saying is the negative of the absolute value of 7 equals negative 7. Or negative 1 times the absolute value of 7 is equal to negative 7. Let's look at one more similar to that, but this time we have A equaling a negative number. So let's write what A is up here again. So we have a negative absolute value of negative 3. Well, what does that equal? Well, this will help to figure out what A is. So A, Damaris, what is A? Right, negative 3. Our A is negative 3. So, as we're working through this, what do we do first? Grouping symbols, absolute value. So we are looking at the absolute value of negative 3. Well, what is the absolute value of negative 3? Our A is negative 3, so it fits this second condition. So therefore, the absolute value of our A is equal to negative of that A. And we got a lot of negative signs going on. So we're just dealing with this absolute value part. We have, based on our algebraic definition, the absolute value of negative 3 is negative. Substitute in A, negative 3. Now, what is negative times negative 3, or negative 1 times negative 3? That's a positive 3. That makes sense. So what we're saying is the absolute value of negative 3 is equal to 3. Geometrically, negative 3 is the distance of 3 away from 0. But we have to bring down our negative sign. Negative 1 times 3 is negative 3. So again, we have a negative answer. But what we're not saying is that the absolute value of negative 3 is negative 3. Rather, we're saying negative 1 times the absolute value of negative 3 is equal to negative 3. The absolute value of negative 3 was the first thing we had to figure out, and that was based on our algebraic definition and our geometric understanding, positive 3. But then we have to bring down our negative sign and follow through, and we get the final answer of negative 3. Now that we've got a geometric understanding of absolute value and an algebraic definition to work with of absolute value, let's explore absolute value and look at some of its properties. Property 1 we're going to look at, we've already talked about. We noticed that the absolute value of A, remember A is any real number. We'll be talking about A's and B's, and again, we're saying number unqualified is a real number. So any A and B that are real numbers, the absolute value of A is always greater than or equal to 0. We saw that geometrically is true because it is relating to the distance on a number line, the distance from the number a to 0. Distance is always positive, therefore absolute value is always positive. Algebraically, we saw it work out as well, as if a is greater than or equal to 0, then the absolute value of a is simply a. If a is less than 0, then the absolute value of a is equal to negative a, which of course a would be a negative number. A negative times a negative is a positive. So algebraically, we see that absolute value is always positive as well. Just but for a few more examples, if a is 3, then the absolute value of a of 3 is equal to, well, in this case, a is greater than or equal to 0, so the absolute value of a is simply a. A is 3. So the absolute value is 3, a positive number greater than or equal to 0. Distance-wise on a number line, we see that 3 is the distance. 3 from 0, distance is always positive. If a is negative 3, again, then based on our algebraic definition, the absolute value of negative 3 will be negative a, because a is less than 0. So what is negative a? Well, a is negative 3. A negative times a negative 3 is equal to a positive 3. So again, we see that the absolute value is positive. It is greater than or equal to 0. And again, geometrically, negative 3 is the distance 3 from 0. It's just like 3 is the distance 3 from 0. Distance is always positive. So property number 2 that we're going to look at states this. The absolute value of negative a is equal to the absolute value of a. All right? Let's take a few examples. Let's test this out. And we won't prove these necessarily, we'll just demonstrate through examples the consistency of them. So our first example, let's let a be a positive number, 9. So what we're saying is the absolute value of a, or excuse me, negative a in this case is 9. So remember, anytime you substitute, use parentheses to avoid error. So the absolute value of negative a, or in this case negative 9, is equal to the absolute value of just good old a. In this case, a is 9. Well, is this a true statement? Let's evaluate it. Let's take this first one. So the absolute value of negative 9 is what? Well, geometrically, 9 is the distance of 9 from 0. Distance is always positive, so it would be a positive 9. Algebraically, we would see that in this case, a is less than 0, so the absolute value of a is negative a, so a negative 9 is a positive 9. So the absolute value of negative 9 is simply 9, a distance of 9, geometrically speaking. Well, is that equal to the absolute value of positive 9? Well, geometrically, yes, the distance from 0 to 9 is positive 9. And algebraically, in this case, a is greater than or equal to 0. So therefore, the absolute value of a is simply a, 9. We have a true statement. 9 is equal to 9. It was consistent with this example. Let's look at this second example. We'll let a equal a negative number. See if this holds. If a is negative 5, does this statement hold true? Well, let's take a look. Let's substitute in. So the absolute value of negative a is negative 5. I hope you're seeing the importance of substituting with parentheses. Is that equal to the absolute value of a, negative 5? Let's simplify these first. So we have a negative times a negative 5 is equal to the absolute value of a negative 1 times a negative 5. 5, absolute value of 5, is that equal to the absolute value of negative 5? I hope you're paying attention with these, as you see how this negative a, when a was positive, it made a negative number. When a is negative, then a negative times a negative, or a negative negative, is a positive. So is the absolute value of 5 equal to the absolute value of negative 5? Well, if you're following so far, and if this is review, which I'm sure it is, then yes, of course, the absolute value of 5 is equal to the absolute value of negative 5. But just, we'll go through it one more time geometrically. The distance from 5 to 0 is 5. The distance from negative 5 to 0, or 0 to negative 5, is again positive 5. Distance is positive. Algebraically, based on our absolute value definition, a is 5. Therefore, the absolute value is equal to a. The absolute value of 5 is equal to 5. And in this case, a is less than 0. So the absolute value of a is equal to negative a. In this case, a negative 5. A negative negative 5 is a positive 5. So again, we have a true statement that 5 is equal to 5. Let's look at a few more properties. The third property we're going to look at is the absolute value of A times the absolute value of B is equal to the absolute value of A times B. Again, A and B are real numbers. So let's again look at a few examples. In this case, we have two variables we're looking at. So we've noticed that positives and negatives are important to see how they play with absolute value. So what we'll do is our first example, we'll have two numbers where A and B are both positive. Next example, A and B are both negative. And then the next example, A and B, one is positive, one is negative. And because we're dealing with multiplication, a positive times a negative is a negative, and a negative times a positive is a negative. And as we look at the properties of real numbers in the next few lessons, this will make a little bit more sense. We really don't have to go through a case where B is positive and A is negative. One example will suffice for those. So let's start with this first example. A is equal to 2, B is equal to 3. Let's see if this property holds as we work through these. So again, we'll substitute in. So the absolute value of A is 2, times the absolute value of B is 3, is equal to the absolute value of A times B. Let's see if that holds true. The absolute value of 2, and I think I'll quit being redundant at this point and talk geometrically and algebraically. I think we're familiar enough with this now. We can simply look at the absolute value of 2 and say that it is 2, understand geometrically and algebraically why it is so. Similarly with a negative, if this was negative 7, we would look at it and be able to say the absolute value of negative 7 is positive 7 and understand geometrically why that is so and algebraically why it is so. If you're still a little fuzzy, maybe particularly with the algebraic portion, I'd encourage you to work through the beginning part of this lesson again until you're comfortable with it. So the absolute value of 2 is 2 times the absolute value of 3 is 3. 2 times 3 is 6. All right, let's work on this side. So absolute values, we work with inside of those first. Those are like parentheses or brackets, grouping symbols. So 2 times 3 is 6. So we have the absolute value of 6 is 6. Is 6 equal to 6? Well, it sure is. So this first example, it holds where A and B are positive. Let's check out the next example. In this case, A is negative 4, so we have the absolute value of negative 4 times the absolute value of B, which in this example is negative 5. Is that equal to the absolute value of A, negative 4, times B, negative 5? Well, let's work through and find out. Absolute value of negative 4 is 4 times the absolute value of negative 5 is 5. 4 times 5 is 20. 20 or 20?
20.
20 in Espanol. And let's work through this side. If this property holds with this example, we should get 20 over here as well. To work with in the absolute value, we have negative 4 times negative 5. Again, a negative times a negative is a positive. So the absolute value of 20 is 20. Again, we have a true statement. So far, so good. Let's work through our last example with this property where we have one negative and one positive. Okay, in this case we have A equals 6, B equals negative 7. So the absolute value of A, 6, times the absolute value of B, negative 7, is that equal to the absolute value of A, 6 times B, negative 7. Alright, same thing. Absolute value of 6 is 6, times the absolute value of negative 7 is 7. 6 times 7 is 42. This side, work within the absolute value. 6 times negative 7 is a negative 42. Absolute value of negative 42 is 42. Again, another true statement. This property holds. Now, these are important to remember. These really help as you're simplifying or working with more involved problems down the road. More involved than we will at this stage in our exploration of absolute values. But remember, the absolute value of A times the absolute value of B is equal to the absolute value of A times B. Let's look at another property. Property number 4. We're looking at quotients. Got a nice little breeze here as we work through these last two properties. So the absolute value of A divided by the absolute value of B is equal to the absolute value of A divided by B. Interesting. Let's see if this one holds. If so, then this can be a very useful property in a variety of contexts. So again, we'll use 3 examples, one in which A and B are positive, one in which A and B are both negative, and then one in which A and B are, one is positive, one is negative, and again, A and B are real numbers. So our first example, we have A equals 6, B equals 3. So the absolute value of 6 over the absolute value of B, 3, is that equal to the absolute value of the quotient A, 6 over B, 3. All right, we work above and below the fraction bar, right? So we have the absolute value of 6 is 6 over the absolute value of 3 is 3. Over here we have the absolute value of 6 divided by 3. Remember, we work within the absolute value. 6 over 3. Another way to look at that is 6 divided by 3, or 6/3. Let's simplify that. So 6 divided by 3, or a simplified 6/3, is what? 2. There's an operation in between these absolute value bars. So here we have 6 over 3 is equal to the absolute value of 2. Well, again, we have 6 over 3 simplifies to 2. Is that equal to the absolute value of 2? 2. Yes, it is. 2 is equal to 2. That holds when both A and B are positive. Let's check out if both are negative. So in this example, we have A equals negative 8, B equals negative 2. Let's substitute in using parentheses. So we have the absolute value of negative 8 over the absolute value of negative 2 equals the absolute value of negative 8 over negative 2. All right, and I got ahead of myself last example. We'll work through just one side at a time like we should, just to be careful. So the absolute value of negative 8 is 8 over the absolute value of, I forgot my absolute value bars. The absolute value of negative 2 is positive 2. So we have 8 over 2, which is 4. So we have 4. Let's see if this side equals 4. We've got an operation to do before the absolute values. So negative 8 divided by negative 2 is a positive 4. Absolute value of 4 is 4. 4 is equal to 4. Holds for both A and B when they're both negative. Let's try A and B where one is negative, one is positive. All right, A, we have negative 12. B, we have positive 4. So we have the absolute value of negative 12 over the absolute value of 4. Is that equal to the absolute value of negative 12 over positive 4? Again, we'll start with this side. The absolute value of negative 12 is positive 12 over the absolute value of 4 is positive 4. 12 divided by 4 is 3. This side we have within the absolute value bars, negative 12 divided by positive 4 is a negative number, negative 3. Uh-oh, looks like we're different, but wait, we have to take the absolute value of negative 3, which is a positive 3. 3 is equal to 3. So again, we have this property involving quotients and absolute values as holding by way of these examples. Again, very useful. Try to remember this. Try to remember not just that it works, but some of the examples, and as you work through these, you'll kind of reason why they work. The absolute value of A over the absolute value of B is equal to the absolute value of the quotient A over B. We're going to look at just one more property today. Last one we're going to look at today. Now this property says the absolute value of A plus the absolute value of B is equal to the absolute value of A plus B. Kind of similar to what we've seen with the multiplication and the division with the quotients. So we already saw that those worked, right? So you should probably just take my word for it and move on, save your time the headache to work through these examples and just say, yeah, it holds. I'll caution you on that. Let's work through this and see if it holds. Again, we have examples where A and B are positive, A and B are negative. In this case, we're going to look at two where A is negative and B is positive, A is positive and B is negative. Let's see if this works. Don't just turn off the video right now and then assume that this does. Let's work through it. So our first example, we have A is equal to 3 and B is equal to 5. We'll substitute in the absolute value of 3 plus the absolute value of 5 is equal to the absolute value of 3 plus 5. All right, we'll simplify. We'll start with this side first. The absolute value of 3 is 3. Bring down. Absolute value of 5. Bring down. 3 plus 5 is 8. Let's see how this side turns out. Work within the absolute value first. 3 plus 5 is 8. Absolute value of 8 is 8. We have 8 is equal to 8. So when A and B are positive, and again A and B are real numbers, it holds. All right, let's try if they're both negatives. In this example, we have A is equal to negative 7 and B is equal to negative 8. Let's substitute in the absolute value of negative 7 plus the absolute value of negative 8. Is that equal to the absolute value of negative 7 plus a negative 8? The side first, the absolute value of negative 7 is 7 plus the absolute value of negative 8 is 8. 7 plus 8 is 15. Let's see what we get over here. Work within the parentheses first. Negative 7 plus a negative 8 is negative 15. So we have the absolute value of negative 15, which is a positive 15. Well, that holds too. So I guess maybe you should have listened to me and just taken my word for it and, you know, pause this. I got this. It's holding so far. Let's check out how it works if one's positive and one's negative. The first example we'll look at, we have A is negative, a negative 10, and B is positive, a positive 4. So we have the absolute value of negative 10 plus the absolute value of 4. Is that equal to the absolute value of negative 10 plus 4? Well, let's find out. Absolute value of negative 10 is 10 plus the absolute value of 4. 10 plus the absolute value of 4 is 4. 10 plus 4 is 14. Over here, negative 10 plus 4 is what? If you're at negative 10 and you add 4, you're at negative 6. Absolute value of negative 6 is positive 6. Damari's caught this. This isn't a true statement, is it? 14 is not equal to 6. 14 is not equal to 6. Now we could say 14 is greater than 6, but it's not equal to. So let's note this up here. This side turns out to be greater than this side with this example. Let's star this. With this example, this side, the absolute value of A plus the absolute value of B, turned out to be greater than the absolute value of A plus B. Interesting. Let's look at this one more example. Since this one turned out to be somewhat interesting, let's now have A be positive and B be negative and see what works. So in this example, we have A equals 2 and B equals negative 6. So we have the absolute value of 2 plus the absolute value of negative 6. Is that equal to the absolute value of 2 plus negative 6? Well, let's find out. Or are we going to have another surprise like we did with this example? The absolute value of 2 is 2 plus the absolute value of 6. Absolute value of 6 is 6. 2 plus 6 is 8. Let's see what this side looks like. So in this case, A is positive and B is negative. Well, the absolute value, we do what's in here first. 2 plus a negative 6 is a negative 4. So the absolute value of negative 4 is 4. Uh-oh, this isn't true either. 8 is not equal to 4. It looks quite similar to this last one. This side is greater than, not equal, is greater than this side. So we have this occur again with this example where A is positive and B is negative. So in dealing with addition, what we've noticed by way of example is that when A and B are both positive or both negative, this holds. Camera just died, it got too hot, so I don't know exactly where we were. I guess the camera woman was just a little too hot for it to handle. But what we noticed was that this is true if A plus B is equal to the absolute value of A plus B when A and B are both positive or both negative. But we notice the absolute value of A plus the absolute value of B is greater than the absolute value of A plus B when A and B are positive and negative or negative and positive. So let's rewrite this in a proper way rather than just throughout the whole property. We can write this as, instead of equal or instead of greater than, we can combine these to use our handy symbol greater than or equal to. So we can say the absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. Now this constitutes an accurate way to describe this particular property. Now, as we mentioned before in previous lessons, oftentimes for reasons which we haven't really got into, we like to express things in terms of less than or greater than. So let's express this statement. This is entirely true, but let's express it in terms of less than or equal to. So we have the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. And this property we call the triangle inequality. Perhaps a good exercise you can think about is why this particular property, as we've examined it, why this might be an appropriate name, the triangle inequality. This property again states the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. It is less than in cases where A and B are, one is positive, one is negative. It is equal to in cases where A and B are both positive or both negative. And again, the way we kind of explored it, which is stating the same thing, just in reverse, is the absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. So the properties we looked at for absolute values. The absolute value of A is greater than or equal to 0. The absolute value of negative A is equal to the absolute value of A. The absolute value of A times the absolute value of B is equal to the absolute value of A times B. The absolute value of A over the absolute value of B is equal to the absolute value of A over B. And finally, the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B, the triangle inequality. Okay, now let's use absolute value to evaluate some expressions. Here let's let E equal 12 and F equal negative 4. You'll have a chance to do more of these on your homework. So we want to evaluate this expression, the absolute value of F minus E plus 4 squared over 6 times the absolute value of F. We'll use our order of operations that we reviewed last lesson to help us with this. So first thing we want to do is, of course, substitute in our correct values. We substitute using parentheses. So this is equal to the absolute value of F is negative 4 minus E is 12 plus 4 squared over 6 times the absolute value of F, which is negative 4. All right, so we're going to work separately above and below the bar. We'll start with our numerator. So we have the absolute value of negative 4 minus 12 plus 4 squared. Let's simplify that. We work within grouping symbols. Absolute value are grouping symbols. So we take negative 4 minus 12 is negative 16. Bring everything else down, including our absolute value bars. Working still within absolute value, the absolute value of negative 16 is a positive 16. See where those absolute values have changed this drastically so far. Bring down the rest. Next thing, simplify our exponents. 4 squared is 4 times 4, which is 16. We have 16 plus 16, which is 32. So this is our new numerator. Let's not forget about that. Damaris will help remind us if I do. Let's now work on the bottom. We have 6 times the absolute value of negative 4. Absolute value we do first. Absolute value of negative 4 is a positive 4. 6 times 4, 24. So here's our new denominator. Let's combine these. So we have 32 over 24. Can we simplify this? Well, yes, we can divide both by 8, right? So 32 divided by 8 is 4. 24 divided by 8 is 3. So 4/3 is our final simplified version. Again, we see how absolute value plays in with more than just looking at distance on a number line. We began our discussion with distance on the real number line. Then we looked at absolute value. Now let's kind of complete or go full circle to see how we can use absolute value to help us find distance from any points on the real number line. We looked at finding distance between the origin 0 and either a positive number, a positive point, or a negative number, a negative point. Well, what if we want to find distance between any two arbitrary points, not necessarily 0? Is there a way that we can do it? It is intuitive, I think, but is there a way we can express that algebraically using what we know now about absolute values? Well, of course, it turns out to be yes. So let's spend the last portion of this lesson looking at that. So let's consider any two points, P or Q. Not necessarily the origin, but any arbitrary points, P and Q. Remember, on the real number line, those correspond to real numbers, or coordinates. So any points, P and Q, and their respective coordinates, let's label them A and B. Now again, remember, if we pick specific values for A and B, these will be real numbers. But our points, P, Q, and our coordinates, A and B, what we're saying is we can find distance between points P and Q. So let's go back to familiar territory, and first of all, let's let P, or let's let A be equal to 0. We want to find the distance between an A and a B, where we'll say we'll let A be equal to 0, or in other words, the origin, and B be equal to 5. Now, we know intuitively that if we're driving, our distance between A and B, if A is 0 and B is 5, would be 5. Would be 5 units of whatever particular 5 units. But is there a way that we can write that, express that algebraically, in which we can find any arbitrary A and B? And so, yes, let's use what we know about absolute value. We could say that the distance from A to B, or the distance from point P to Q, is equal to the absolute value of A minus B. Let's try that. We're saying that A is 0, the origin, so we're saying the distance from P to Q, town P to town Q, in this case this is our origin, is equal to the absolute value of A, which is 0 in this case, minus B, which is 5. Well, let's see what that turns out to be. 0 minus 5 is, of course, negative 5. The absolute value of negative 5 is 5. Hey, that turned out pretty well. That's exactly what we said intuitively our distance should be, from 0 to 5. But also, let's think about what we learned from distance. It'll be the same distance whether we start at A or start at P and go to Q as it would be from if we start at Q and go to P. Now, we're heading in the negative direction, but again, we talked about with distance, that doesn't matter. Distance is always greater than or equal to 0. It'll be the same distance heading in the positive direction as it will be on the return trip heading back in the negative direction. So we just as easily could say that the distance from P to Q is equal to the absolute value of B minus A. Now, the absolute value allows both of these statements to be true because absolute value, like distance, is always going to be greater than or equal to 0. So let's try if we start from B and minus A. So in this case, B is 5, and we're subtracting A, which is 0. 5 minus 0 is 5. The absolute value of 5 is 5. So we get the equivalent statement. We intuitively said that our driving distance or our walking distance or whatever our distance between A and B should be 5. Algebraically, we see that with the absolute value of A minus B, we get 5. Or if we start with B and minus A, we get 5. Now notice here that if we left the absolute values off, A minus B would give us a negative 5. B minus A would give us a 5. But the absolute values, which correspond to distance geometrically, allow both of these statements to be true. So now let's try working in the negative direction to see if that works. Okay, now let's let Q be the origin. So the coordinate B would be 0. And now let's just keep the same value, but only in this direction, the negative direction. We'll let A equal negative 5. So let's see if our distance, still working with our familiar origin, comes out to what we say that it should. Again, if we're starting at the origin 0 and going in this direction 5 units, the distance should still be 5, even though we're going in the negative direction. So let's use our expression using absolute value to see if that works. So in this case, we have b equals 0 and a is equal to -5. So the distance from P to Q, or Q to P, would be equal to a, which is -5, use parentheses to substitute, minus our b, which is 0, or the absolute value of b, which is 0, minus the a, which is -5. Okay, so let's evaluate these and see if we're saying intuitively that the distance should still be 5, even though we're dealing with where a is a -5. So a -5 minus a 0 is -5. So the absolute value of -5, again we have 5. That looks good. Let's check if we start with b, and I did substitute 0 in. If we start with b minus a. So in this case, a 0 minus a -5 would be a +5. So notice we're different at this point, but because we're taking the absolute value of 5 is 5, just as the absolute value of -5 is 5, like we saw in our properties. So that works great as long as we allow one of these points to be the familiar origin 0, but let's expand this to any two arbitrary points. Let's look at this example. Let's let a be -3, and we can label that up here. A is -3. B, we'll say, is 11. So what we've been suggesting with this, with our use of absolute value, is that the distance from A to B is the absolute value of either A minus B or B minus A. That's worked great when we were dealing with the origin. But now our 2 points, we're not dealing with the origin. Now we can again, and this is a fairly easy example, intuitively think through this. If we're traveling from P to Q, well, it'll take 3 units, let's just say miles, to get to the origin. So it'll take 3 miles plus from the origin to 11 would be an additional 11. So 3 plus 11 is 14. So intuitively we can come up with that the distance certainly should be 14. But if we expand this and it gets a little bit more complicated or a little bit more involved, we want to be able to algebraically express this so we can substitute values in and have confidence in the algebra that what comes out will be an accurate reflection of the distance. So let's use our expression and see how it works for this example, where a is -3 and b is 11. So the distance from P to Q is equal to the absolute value of a, which is -3, minus b, which is 11, or the absolute value of b, 11, minus a, -3. Let's evaluate this portion first. So a -3 minus an 11 is a -14. Absolute value of a -14 is a +14. Well, that corresponds to what we intuitively thought. Let's see what happens if we use b minus a. 11 minus a -3, 11 minus a -3 would be a +14. I think at this point it's safe to say that we're looking good. The absolute value of 14 is 14. So we can take any two arbitrary points on the real number line and find the distance between them by using absolute value. You'll have some chances to practice this on the homework. Okay, so the last few lessons, we've been looking at some of the qualities or properties of real numbers. Specifically, or namely, the relative relations between points on the real number line, which correspond to real numbers. That is, one is less than another real number, or one is greater than another real number. And now we spent some time in a way to quantize that, to look at how much greater, how much less than, by looking at the distance between two real numbers. and we used absolute value to do this. Now, absolute value has many other uses, and as I mentioned previously, we will be dealing more with absolute value in the future. But for now, let's use it to talk about distance on the real number line. You'll have a chance to work through some of these on your homework, and I look forward to seeing you next time after the homework as we look at some other properties of the real numbers.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.